Hello everyone. So here we shall solve some KCET previous year questions on the chapter thermal properties of matter. Um, uh, and if you have any questions or doubts in the solutions, then please write us in the comments section. We shall clarify them in the subsequent videos. Um, and all the homeworks on every chapter will be uploaded in the Sapience Education application. So please install our Sapience Education application, whose link will be provided in the description. And if you also feel that you have more difficulty in any of the chapters, then also please write the name of that chapter in the comments section so that we can give more priority on it and solve more and more questions on that chapter. So here we shall start with the very first question of the chapter thermal properties of matter. The unit of Stephen's constant is, so according to the Stephen's law, so according to the Stephen-Boltzmann law, according to the Stephen-Boltzmann law, we know that the energy radiated per second, the amount of energy is radiated per second, the energy radiated from a black body. So the Stephen-Boltzmann law is on the black body radiation. So the energy radiated from a black body per second is given as that is E by T, energy radiated per second. So we can say it is energy by time, energy per unit time, that is equal to sigma A T power 4, where A is the surface area of the black body and T is the absolute temperature. A is the surface area and T is the absolute temperature. Absolute temperature means it is the temperature in the Kelvin scale, and sigma is called the Stephen's constant. So therefore sigma can be written as E by T, A T power 4. Here T is the time and E is the energy. So therefore the unit of sigma will be the unit of energy is joule and time is second. So joule per second, it is also called as watt. Joule per second is watt. So the unit of energy per unit time, actually it is called the power also. So the SI unit of power is watt. So it will be watt per meter square per Kelvin power 4. So it is watt meter power minus 2 Kelvin power minus 4. So therefore option C is the correct answer. So if you are unable to understand in any of the steps of the solution, then please write us in the comments section. Then in question number 2, it is told the sprinkling of water reduces slightly the temperature of a closed room because the sprinkling of water reduces slightly the temperature of a closed room because temperature of water is less than that of the room. Okay, specific heat of water is high. Water has a large latent heat of vaporization. Water is a bad conductor of heat. So the correct answer is option C. Since why? Water will absorb more heat. Water absorbs more heat to convert into steam. At 100 degrees Celsius. So it means that so option C is the correct answer, that water has more latent heat of vaporization, latent heat of vaporization. So when water is sprinkled, then due to the large surface area, the rate of evaporation is increased. So water has more latent heat of vaporization. So when water is sprinkled, then the the exposed surface area is also increased. The exposed surface is also increased, due to which faster evaporation takes place. Due to which faster evaporation of the water, and more absorption of heat, takes place. Due to which there is a cooling effect in the room. Due to which the temperature of the water, the temperature of the air in the room decreases. Due to which the temperature of the air in the room decreases. Then here question number 3, it is told two identical rods AC and CB made of two different metals having thermal conductivities in the ratio 2:3 are kept in contact with each other at the end C, as shown in the figure. A is at 100 degrees Celsius and B is at 25 degrees Celsius. Then the junction C is at. Two identical rods AC and CB made of two different metals in thermal conductivities in the ratio this. Two identical rods AC and CB made of two different metals. So their thermal conductivity identical rods. Okay, identical rods, it means their length is the same. And the area of cross section is also the same. And this is A, this is B. Area of cross section is same here and area of cross section is same here, but their thermal conductivities are K1 and K2 since they are made of two different metals. Since different metals will have different thermal conductivities, since the rule is different metals will have different values of K, it means different thermal conductivities. So now point end A is 100 degrees Celsius, this is theta, and this is 25 degrees Celsius. Now here it is told that K1 is to K2, that is 2 is to 3. It means K1, therefore K1 I can take it as suppose 2K, and K2 we can take it as 3K. So what is the temperature of the junction? That is theta, suppose. So this theta we have to find at the point C. What is the temperature theta? So therefore we can say that since they are in series, therefore the rate of conduction of heat is the same. So for conduction of heat we can say that dq by dt, which is the rate of flow of heat, that is equal to Ka dt by dx, Ka delta theta by delta x, Ka delta theta by delta x, where delta x is the length. Okay, so delta theta by delta x is called as the temperature gradient. So now here So here, since they are in series, so dq by dt will be the same. So therefore we can say that k1 into a into delta theta, which is theta minus 100 by delta x, which is L, that should be equal to k2a into 25 minus theta by L. So L and A that will cancel, and k1 is 2k. So 2k into theta minus 100 degree Celsius, that is equal to k2, which is 3k into 25 minus 25 degrees Celsius minus theta. Okay, so k and k will cancel. So this I can write 2 theta minus 200, that is equal to 75 minus 3 theta. So from here we can say that therefore 2 theta plus 3 theta, that is 5 theta. 5 theta will be equal to 75 plus 200, that is 275. So therefore theta will be equal to 275 divided by 5. So theta will be equal to 5 5s are 25 and 5 5s are 25. So this is 55 degrees Celsius. So option A is the correct answer. Okay. So then it is told the surface temperature of the sun, which has maximum energy emission, is 500 at 500 nanometer is 6000 Kelvin. The temperature of a star which has maximum energy emission at 400 nanometer will be. So here we have to apply the Wien's displacement law. So according to the Wien's displacement law, you can say that the formula is lambda m into t, that is equal to b, where b is called as the Wien's constant. And lambda m is the wavelength at which the maximum energy emission takes place. Lambda m is the wavelength at which there is maximum intensity of radiation. At which there is maximum intensity of radiation. The lambda m is the wavelength at which there is maximum intensity of radiation at the absolute temperature T from a given black body, from a black body. Okay, so therefore here it is told that lambda m, surface temperature of sun which has maximum energy emission, is maximum energy emission at okay, so here lambda m is 500 nanometer when the temperature of the surface of the sun is 6000 Kelvin, and then we have to find the temperature T1 at which the maximum energy emission is obtained at the wavelength 400 nanometer. So now therefore lambda m1 I can say, so lambda m1 into T1, that is equal to lambda m2 into T2, since that is constant. So therefore we can say that lambda m1, that is 400 nanometer, into T1 that we have to find, that is equal to lambda m2, which is, say, this is lambda m2, this is T2. So this is 500 nanometer into T, which is 6000 Kelvin. So here nanometer and nanometer will cancel, and 400 and 00 will cancel. Then we can say that T1 will be equal to 5 into 60 into 100 divided by 4 Kelvin. 5 into 60, 100 divided by 4. So 15 4 is 60. So 15 5 is 75. So 7500 Kelvin T1. Yes. So option C is the correct answer. Option C is the correct answer. Then it is told that the coefficient of the thermal conductivity of copper is 9 times that of steel. Thermal conductivity of copper is 9 times the thermal conductivity of steel. In the composite cylindrical bar as shown in the figure, what will be the temperature at the junction of copper and steel? At the junction of copper and steel, this one. This is 100 degrees Celsius, this is 0 degrees Celsius. This will be 18 centimeter. This is 6 centimeter. Now this is copper. This is steel. Now what will be the temperature at the junction? Let it be theta. So that we have to find. So therefore we can say that since they are kept in series, therefore the rate of flow of heat will be thermal flow of heat by thermal conduction will be the same. So it means that dq by dt, which is equal to k of copper into, so the area of cross section is the same actually. Area of cross section is same. So ka delta theta, which is theta minus 100 divided by this is 18 centimeter. That is also equal to k into steel into area into 0 degree minus theta divided by 6 centimeter. So these two are same. So therefore we can say that k of copper, that is 9 times the k of steel, 9 times the k of steel into A into theta minus 100 divided by 18 centimeter, that is equal to the thermal conductivity of steel into A into 0 minus theta divided by 6 centimeter. So k of steel will cancel, A and A will cancel, centimeter will cancel, 6 3s are 18, then 3 3s are 9. So this will be 3 into theta minus 100, that is equal to 0 minus theta. So this will be 3 theta minus 300, that is equal to minus theta. So therefore we can say 4 theta will be equal to 300. So therefore theta will be equal to 3 into 100 divided by 4. So 4 25 is 100. So 25 into 3, that is 75 degrees Celsius. So option C is the correct answer. So it means the temperature at the junction of copper and steel should be 75 degrees Celsius. Then it is told that second. Okay, just a second. Okay, then in question number 6 it is told that if a black body emits 0.5 joules of energy, 0.5 joules of energy per second, when the temperature on it is 27 degrees Celsius, then the amount of energy emitted by it when it is at T1, which is 627 degrees Celsius, then how much energy will be emitted by it per second? How much will be the energy emitted joule per second? That will be how much when T1 is this. Okay, so according to the Stephen's law of black body radiation, we know that according to the Stephen-Boltzmann's law, Stephen-Boltzmann law of black body radiation, Stephen-Boltzmann law of blackbody radiation, we can say that uh, the rate of emission of heat, means energy emitted per unit time, that is given as sigma a t power 4 by a black body, where T is the absolute temperature of the black body and A is the surface area of the black body, and sigma is called as the Stephen's constant. So now here it is given that the rate of flow of heat, that is 0.5. So from here we can say that sigma is constant, so therefore we can say that E by T means E1 by T1 divided by A1 into T1 power 4, that will be equal to E2 by T2, E2 by T2 by A2 into T power 4, T2 power 4. Since why that is equal to sigma, which is constant always. Now area is constant, so that is 0.5 joule per second divided by A. The area of the cross section area of the black body, so sorry, the surface area of the black body will not change, that will be the same. So T1 is this, so we have to convert into the absolute scale. So T will be equal to 273 plus 27, that is equal to 300 Kelvin, and 627 plus 6 T1 we have to find in absolute scale, that is 627 plus 273, so that will be 73 plus 27, so that is 100 plus, so 2 plus 6 is 8 plus 1, this is 900 Kelvin. So this will be A into T1 power 4, so that is 300 power 4, that will be equal to the rate of flow of heat that is asked, the rate of emission of heat is asked, so let it be E2 by T2 that we have to find. So that is A, since A1 equal to A2, that is equal to A, since the black body is the same, it is not getting changed, since the black body remains the same, since the black body is not changing in shape or size, it's not changing its shape or size, so therefore this will be A into 900 whole power 4. So therefore E2, A and A will cancel, so E2 by T2, that will be equal to 900 by 300 whole power 4 into 0.5 joule per second. So this will be 0 will cancel, 3 3s are 9, so 3 power 4, that is 81 into 0.5 joule per second. So that will be equal to, so 5 ones are 5, 5 8s are 40, so 40.5 joule per second. So it means that per second now the energy will be emitted. So when the temperature of the black body is 627 degrees Celsius, then the rate of energy emission will be 40.5 joule per second. So option C is the correct answer. Then here it is told that 0.1 meter cube of water, 0.1 meter cube of water which is at 80 degrees Celsius is mixed with 0.3 meter cube. Here we have 0.3 meter cube of water which is at 60 degrees Celsius. Then the final temperature of the mixture is. So therefore the final temperature of the mixture So according to the principle of calorimetry, we can say that according to the principle of calorimetry, when cold body, when cold body is mixed with hot body, when cold body is mixed with hot body, then heat lost by hot hot body, that is equal to the heat gained by the cold body, is equal to the heat gained by the cold body. So let the final temperature of the mixture be let the final temperature of the mixture be theta, mixture be theta degree Celsius. So now therefore the heat lost by the hot water, heat lost by the 80 degree Celsius temperature water, that will be um, H equal to ms delta T. So mass equal to density into volume. So the density of the water will not change, that will remain the same. So mass will be density now density of water, that is equal to 1010 power 3 kg per meter cube. So therefore 0.1 meter cube, therefore the mass will be 0.1 density into volume, so volume into density. So 0.1 into 10 power 3 into S, the specific heat of water. Let the specific heat be SW. Now, okay, so let the specific heat capacity, specific heat capacity of water be SW. So we know that the specific heat of water is 1. Okay. Okay, so let the specific heat of water be SW joule per kg per Kelvin. Joule per kg per Kelvin. Since we know that H equal to ms into T. Mass into specific heat into temperature, that is equal to the amount of heat, or delta H equal to ms delta T. So this will be SW into heat lost, so that will be, so temperature decreases, so this will be 80 minus theta, and heat gained by the 60 degree Celsius water, so that will be also mass, which is volume into density into specific heat into theta minus 60 degree, since theta will be some temperature which should be greater than 60 degree Celsius and less than 80 degree Celsius. Since when 60 degree Celsius and 80 degree Celsius water are mixed, then the equilibrium temperature means the final temperature of the mixture at thermal equilibrium, that will be obviously some temperature which is in between 60 and 80, since which will be more than 60 and less than 80. So therefore if we apply the principle of calorimetry here, then therefore we will get 0.1 into 10 power 3 into SW into 80 minus theta, 80 degree minus theta, so that will be equal to 0.3 into 10 power 3 into SW into theta minus 60 degree. So SW will cancel, 10 power 3, 10 power 3 will cancel. So 0.1, 0.1, this point will cancel. So this is 80 degree minus theta. So that will be 3 into theta minus 360, theta minus 60. So this will be 80 minus theta, that is 3 theta minus 360, 18. So 4 theta will be equal to 180 plus 80, that is equal to 260. So therefore theta will be equal to 260 by 4. So theta will be equal to 4 6 are 24 and 4 5 are 20. Theta equal to 65 degrees Celsius. So theta is 65 degrees Celsius. So the final temperature of the mixture is 65 degrees Celsius. So option A is the correct answer. So in any of the solutions, if you are unable to understand any of the steps or any other doubts you are having, then please write us in the comment section. Then here it is told the amount of heat energy radiated by a metal at temperature T is E. The amount of heat energy radiated by one metal is there. The amount of heat energy that is radiated at temperature T is E. When the temperature is increased to 3T, at 3T, how much energy will be radiated? So therefore we can say that by the Stefan-Boltzmann law, for any body, we can say that the energy which is radiated per unit time, that is given as the sigma E A T power 4, where E is the emissivity of that metal, where E is the emissivity of the body, which is constant for that particular body. Emissivity of the body which is being used. So for different bodies the emissivity will be different, but if the body is not changing, means if the material does not change, if the material is not changing, then the emissivity also will not change. So sigma into E, this entire thing is a constant actually. Sigma is Stephen's constant and E is the emissivity, which for a given material it is a constant. So therefore the energy radiated, we can say it is sigma E A T power 4 into T into time. So therefore we can say that sigma E, that is constant, so E by, and the time is also constant, so therefore E by A T power 4, that is constant, and the area also will be constant only. So sigma, so E by T power 4, that will be constant. So therefore we can say that E1 by T1 power 4, that will be equal to E2 by T2 power 4. So therefore here energy is E when the temperature is T, so E by T power 4, that will be equal to how much energy will be radiated, E dash divided by T2, that is 3T power 4. So therefore E dash will be equal to 3T by T whole power 4 into E. So this will be 3 power 4, that is 81 E. So 81 E is the answer. So 81 times of the energy will be radiated when the temperature of that metal is increased to 3 times the initial temperature. So option A is the correct answer. Then here it is told the surface temperature of the stars is determined by using. So the surface temperature of the stars is determined by using the Wien's displacement law. Since why, if we from the star, first we have to observe that what is the wavelength of the radiation which is being radiated by it. First we have to find the wavelength of radiation that which has maximum intensity. The wavelength of radiation which has maximum intensity, which is radiated by the star, which is emitted by the star, sorry, which is emitted by the star. So we have to observe the wavelength of radiation which has maximum intensity and which is emitted by that star, and that we will say that is equal to lambda m, and we know that lambda m into t, that is equal to b. B is the Wien's constant. So from there t we can find out by b by lambda m. So from there we can find out how much is the surface temperature of the star. Here the Wien's constant is 2.898 into 10 power minus 3 meter Kelvin. Okay. So it means by using Wien's displacement law only we can find the surface temperature of the star. So option B is the correct answer. Then it is written two slabs are of thicknesses d1 and d2. Their thermal conductivities are k1 and k2. They are kept in series. So two slabs are there. Their thicknesses are d1 and d2. They are kept in series and their thermal conductivities are also k1 and k2. The free ends of the combination of these two slabs are kept at temperatures theta 1 and theta 2. The free ends. Assume that theta 1 is greater than theta 2. The temperature of their common junction, this theta, that will be how much? So the thicknesses are d1 and d2. So let's say their area of cross section should be assumed to be same, since why it is not mentioned anything about their area of cross section. So we should assume that the area of cross section is same for both. So therefore by the rule of thermal conduction, by the principle of thermal conduction, we can say the rate of flow of heat will be the same since they are kept in series. So dq by dt is the same, will be the same since they are kept in series. So therefore dq by dt, so that will be equal to k1a delta theta, which is theta minus theta 1, by delta x, which is d1. So that will be equal to k2 into a to theta 2 minus theta divided by d2. So therefore these two are same. So therefore we can write k1a theta minus theta 1 by d1, that is equal to k2a theta 2 minus theta by d2. Okay. This we have to find. So therefore a and a will cancel out. Then we can say that k1 by d1 into theta plus k2 by d2 into theta, that will be k2 theta 2 by d2 plus k1 theta 1 by d1. So from here we can say that theta into k1 by d1 plus k2 by d2, that will be equal to k1 theta 1 by d1 plus k2 theta 2 by d2. So theta will be equal to k1 theta 1 by d1 plus k2 theta 2 by d2 divided by k1 d1 plus k2 by d2. So this we have to simplify. So if we take the LCM, this will be k1 theta 1 d2 plus k2 theta 2 d1 divided by d1 d2 divided by, this will be k1 d1 k1 d2 plus k2 d1 divided by d1 d2. So d1 d2 will cancel. So therefore the temperature at the junction, it is asked to find the temperature theta of the common junction. So that will be k1 theta 1 d2 plus k2 theta 2 d1 divided by k1 d2 plus k2 d1. k1 d2 plus k2 d1, k1 theta 1 d2 plus, okay, so option C is the correct answer. Option C is the correct answer. Then it is told hot water cools down. Hot water cools down from 60 degrees Celsius to 50 degrees Celsius in a time interval delta t1 of 10 minutes, and from 50 degrees Celsius, so we can write like this: from 60 degrees Celsius to 50 degrees Celsius it cools down in time interval 10 minutes, and from 50 degrees Celsius to 42 degrees Celsius in the time interval of next 10 minutes. Then the temperature of the surrounding is how much? What is the temperature of the surrounding? Let the temperature of the surrounding is theta s. So let theta s be the temperature of the surrounding. So then according to the Newton's law of cooling, according to the Newton's law of cooling, we can say that theta 2 minus theta 1 by T, where theta 2 is the final temperature and theta 1 is the initial temperature, and T is the time interval which is required to cool down from theta 1 to theta 2. Cool down from theta 2 to theta 1, sorry, okay. So that will be equal to, so theta 2 minus theta 1 by T, that will be equal to K into theta 1 plus theta 2 by 2 minus theta s, where theta s is the temperature of the surrounding. So that only we have to find. So therefore here it is told that from 60 degree to 50 degree, so this will be 60 minus 50 by 10 minute, and this is in degree Celsius, so that is equal to K into theta 1 plus theta 2, that is 60 plus 50 by 2 minus theta s. So here actually there are two unknowns, so we need two equations, and it is also told that it cools down from 50 to 42 also in the next 10 minutes. So this is 10. So therefore here we can see K into, this is 110 by 2, K into 110 by 2 minus theta s, that will be equal to 10 by 10. So this is 10 by 10 degrees Celsius per minute. So this is in degrees Celsius only. So K into 55 degrees Celsius minus theta s, so that will be equal to 1 degree Celsius per minute. This is coming. And then also we can see that 52 degrees Celsius, 50 degrees Celsius minus 42, 50 minus 42 by 10 minutes, and this is in degrees Celsius, so that is equal to k into 50 plus 42 by 2 minus theta s. So k is equal to this, okay. So k into this will be 92. So this will be 2 4s are 8, 2 6 are 12. This 25 plus 21, so 46 minus theta s, 46 degrees Celsius minus theta s, so that will be equal to, this is 8 by 10, so that is 0.8 degrees Celsius per minute. So therefore from here, if we take the ratio of these two, then k will get cancelled. Then we will have 55 minus theta s divided by 46 minus theta s. So that will be equal to 1 by 0.8. K gets cancelled. From here theta s we can find. So this will be 55 minus theta s divided by 46 minus theta s. So that will be equal to 1 by 0.8 means 8 by 10. So this is 10 by 8. So 4 2 is 8, 2 4 is 8, 2 5 is 10. So then we will cross multiply. So this will be 4 5 is 20, 4 5 is 20, 22 minus 4 theta s minus this will be 5 into 46, that is 5 6 is 30, 5 6 is 30, 5 4 is 20, 23 minus 5 theta s. So this will be 5 theta s minus 4 theta s, that is theta s, that will be equal to 230 minus 220, so that is 10. So theta s will be equal to 10 degrees Celsius. So the temperature of the surrounding is 10 degrees Celsius. So option D is the correct answer. But then here it is told 3 identical rods A, B and C are placed end to end. 3 identical rods A, B and C are placed end to end. 3 identical rods are there, A, B and C, they are placed end to end. A temperature difference is maintained in between the free ends A and C. The thermal conductivity of B, is thrice of C. Thermal conductivity of B, it is told thermal conductivity of B, that is equal to, this is KB, this is KA is the thermal conductivity of A. KB is suppose thermal conductivity of B and KC is suppose thermal conductivity of the rod C. So KB is thrice of that of C, so 3 into KC, and that is also equal to conductivity of B and half of that of A, so half of KA. So let's say that is equal to K, suppose, or yeah, that is equal to K, say. So therefore KA, that will be equal to 2K, and KC, that will be equal to K by 3. The effective thermal conductivity of the system will be, Ka is thermal conductivity of rod A. Okay, so we have to take thermal conductivity of in terms of Kb and Kc, we have to express in terms of Ka actually. So this we can't take. We have to write Kb and Kc in terms of Ka only. So therefore we can see that Kb, that is equal to Ka by 2, and Kc, that is equal to Ka by 6. Effective thermal conductivity of the system. Now we know that dq by dt, the rate of flow of heat by conduction, that is equal to Ka delta theta by delta x. Now this is equal to delta theta by delta x by Ka. Now this delta x by Ka, this is called as the thermal resistance. Thermal resistance, which acts similar to the electrical resistance. So when they are kept in series, then the equivalent resistance, the equivalent thermal resistance, equal to the sum of the resistances of A, B and C. So therefore I can say that, so their lengths are also same, L, L and L, and their area of cross sections are also same. So therefore I can say, and that is this will be equivalent to one single rod whose effective thermal conductivity is suppose K effective, and its length will be 3L, and area of cross section will be A only. So this whole system of three identical rods can be replaced by a single rod, which is having length 3L. So therefore R equivalent, that will be equal to 3L by K effective into A. So that will be equal to RA, that will be equal to L by KA into A. Let's say the area of cross section is suppose A1. Okay, area of cross section is A1, plus that will be L by KB into A1, plus that will be L by KC into A1. So L by A1 all will cancel out. So then from here you can say 3 by K effective, that is equal to 1 by KA plus 1 by KB. So KB is KA by 2, plus this is 1 by KC, that is KA by 6. So therefore 3 by K effective, that will be equal to 1 by KA plus this is 2 by KA plus this is 6 by KA. Now from here we can say 3 by K effective, that will be equal to, the LCM is KA, and this will be 1 plus 2 plus 6, which is 9. So 9 into K effective, that is equal to 3 into K. We are doing cross multiplication. So K effective will be equal to 3 into KA by 9. So 3 3s are 9. So therefore K effective will be equal to KA by 3. KA by 3. K effective is KA by 3. So option A is the correct answer. A is the correct answer. Then in question number 13 it has been told, the quantities of heat required to raise the temperatures of two copper spheres of radii R1 and R2. So R2, suppose this is R2, and R1, this R1 is equal to 1.5 R2 through 1 Kelvin. The quantities of heat required to raise their temperatures by 1 Kelvin. So here delta T, that is 1 Kelvin for these both. The rise in temperature should be 1 Kelvin. Now therefore are in the ratio. The quantities of heat required, when suppose here the heat required is delta Q1, here the heat required is delta Q2. So therefore we know that delta Q, that is equal to ms delta T. Now both are made of copper, so the specific heat capacity will be the same. So specific heat capacity is the same. Specific heat capacity depends on the material of the body. Specific heat capacity depends on the material by which the body is made of. Specific heat capacity of a body depends on the material by which the body is made of. Depends on the material by which the body is made of. The body is made of. So specific heat capacity, let that be S. Let the specific heat capacity be S, and M is the mass of the body, and delta T is the rise in temperature, and delta Q is the amount of heat to be supplied, the amount of heat that is required. So we can say that the specific heat capacity will be the same for both, same for both the spheres, So therefore delta Q1, that will be equal to M1. Now mass is equal to volume into density. Now the density also will be the same. Since both are made of both are made of copper. Both are made of copper only. So their density will be the same, but their volume is not same. So this will be m1 into s1 into delta t. So here, therefore, we can say that s1 that will be equal to s2 that is equal to s, suppose say, and delta q2 also will be equal to m2 into s2 into delta t. Now delta t is the same of obviously since both the spheres are since the temperature of both the copper spheres should be raised by 1 Kelvin only. So now therefore mass m1 is mass of the first sphere, so that is volume v1 into rho, so that is volume which is 4 by 3 pi r1 cube into rho, and m2 will be v2 into rho, that is 4 by 3 pi r2 whole cube into rho. Now therefore delta q1 by delta q2, their ratio we have to find. Delta q1 by delta q2, that will be m1 which is 4 by 3 pi r1 cube into rho 1 or rho into s into delta t divided by 4 by 3 pi r2 cube into rho into s into delta t. So this will be equal to rho s delta t will cancel, 4 by 3 pi will cancel. So this is r1 by r2 whole cube. So now here it is told r1 equals to 1.5 r2. So this is 1.5 r2 divided by r2 whole cube. So this is 1.5 whole cube. This will be 3 by 2 whole cube. So that is 27 by 8. 27 by 8. So option A is the correct answer. So the ratio of the heats that is required to raise the temperature of the copper spheres by 1 Kelvin is 27 by 8. Then the question number 14 is, which of the following is VMT graph for perfectly black body? Which one of the following is sorry, it is not VM, it is nu m. Nu m it is called, so nu m is the frequency of radiation. Frequency of radiation with maximum intensity. Frequency of radiation having maximum intensity. And T is the absolute temperature. T is the absolute temperature of the body. So now according to the Wien's displacement law, we know that according to the Wien's displacement law, we know that lambda m into T that is equal to B, where lambda m is the wavelength corresponding to the wavelength of radiation which corresponds to the maximum intensity. Now we know that frequency that is equal to c by lambda, where c is the speed of light in vacuum, or c we can say it is the speed of any electromagnetic radiation, in vacuum, yeah. So therefore we can say that lambda will be equal to c by nu. So we can say that this will be, so therefore lambda m will be equal to c by nu m. Hence we can say that c by nu m into T that is equal to B. So therefore nu m that will be equal to c by B into T. Now c is a constant which is the speed of light in vacuum, and B is Wien's constant, so that is also constant. So c by B is a constant. So therefore we can say that nu m is directly proportional to the absolute temperature. It means the frequency that corresponds to the maximum intensity of radiation, that is proportional to T. So it means the graph of nu m versus T will be a straight line passing through the origin. Will be a straight line with having slope straight line having positive slope, which is c by b, and which is passing through the origin, passing through the origin. So therefore you can see that for option C, so the graph C is the straight line which is passing through the origin. So option C is the correct answer. Option C is the correct answer. Then we shall solve the last question of this class, and the remaining question we shall continue in our next part of this chapter. Okay, so here it is told that A, B and C are the three identical conductors but made from different materials. It means the materials, therefore the materials A, B and C are different actually. The materials A, B and C are different. They are not same. They are kept in contact as shown. So they are kept in contact, A, B and C. And this end is at 100 degrees Celsius. The free end of A is at 100 degrees Celsius and the free end of C is 0 degrees Celsius. And their thermal conductivities are K, 2K and K by 2. It means K of A is K and thermal conductivity of B is 2K and thermal conductivity of C is K by 2. Then during steady state, the temperature of the junction of A and B. What should be the temperature of these two junctions? Let's say this is theta 1 and this is theta 2. So what should be the temperature at these junctions that we have to find? So now here, so now since they are connected in series, since the thermal conductors are connected in series, they are connected in series, so the rate of flow of heat will be the same. So the value of dq by dt, which is the rate of flow of heat by thermal conduction, that will be the same. Rate of flow of heat by thermal conduction will be same. So now therefore, that is dq by dt. So that will be for these. So if we apply dq by dt in between the endpoints of A, then we will have, that is Ka. Now the area of cross section will be the same. Let's say the area of cross section, we take it as A1. So Ka1 into dt delta theta by delta x, that is theta 1 minus 100 by length. So the lengths are also same, identical conductors. Length L, let's say the length is L for all, the length is L. So this will be this Ka1 into, this will be theta 2 minus theta 1 by L. Now this is 2K actually, and this will be K by 2 into A1 into 0 minus theta 2. Sorry, this will be theta 1 minus 100, 0 minus theta 2 divided by, this is L. So this we have to solve, and then we can find the values of theta 1 and theta 2, which are the temperatures at the junction points A and B, at the junction of A and B. Okay, so the temperature at the junction of A and B, it means that theta 1 only we have to find. We have to find theta 1. Theta 1 is asked. Theta 2 is not asked. So somehow we have to eliminate theta 2. So therefore we can see that it is Ka1 by L into theta 1 minus 100, that is equal to 2Ka1 by L into theta 2 minus theta 1. So that will be equal to k a1 by 2 into L to 0 minus theta 2. So therefore we can cancel this k a1 by L on all sides. So then we will have theta 1 minus 100, that is equal to 2 into theta 2 minus theta 1, that will be equal to minus theta 2 by 2. So therefore, so if we solve these two, then we will get minus theta 2 by 2, that is equal to 2 into theta 2 minus 2 theta 1. So therefore we will have 2 theta 2 plus 2 plus theta 2 by 2, that is equal to 2 theta 1. So therefore we will have 2 to the 4, 4 plus 1 5, 5 theta 2 by 2, that is equal to 2 theta 1. So therefore theta 2 will be equal to 4 theta 1 by 5. Now if we equate these two equations, the first and the last equations, so therefore we'll have theta 1 minus 100, that is equal to minus theta 2 by 2. So therefore theta 2 by 2, that is equal to obviously 2 theta 1 by 5. So therefore we can have theta 1 minus 100, that is equal to minus 2 theta 1 by 5. Therefore you can say theta 1 plus 2 theta 1 by 5, that is equal to 100. So therefore 5 theta 1, so this will be 5 plus 2 7 theta 1 by 5, that is equal to 100. Now therefore theta 1 will be equal to 500 divided by 7. So that is how much? That is 7 7s are 49, then 10, so 7 1s are 7, then 30, then 7 4s are 28, 7 3s are 21. So it is approximately 71.43 degrees Celsius. 71.43 degrees Celsius. So it is so the closest answer is option A. Option A is the correct answer. So hope you have understood the solutions of these questions from 1 to 15. So if any doubts are there in any of the questions or in any steps of the solution, then please write us in the comments section, and please install our Sapience Education application, whose link has been provided in the description, from where the homeworks on every chapter will be uploaded, which you can solve them, and which shall be helpful for your KCET exam. And if you feel that some chapter is more difficult for you, then also please write the name of that chapter in our comments section. So here we shall end our class. So thank you everyone.